Okay, welcome to class, everyone. Happy Friday. Okay, we're going to talk about a super cool subject today, which is Weibull Statistics. Anybody heard of Weibull Statistics? Have you seen this in other classes? No? Okay. This is useful stuff. What we did to start with is I asked our front row Joes to grab some rubber bands, 5 millimeters apart, so they would clamp onto it, their little thumbnails, 5 millimeters apart, and then they put fingertips at risk, and they just stretched this thing as far as it would go until it fractured, right? The rubber band. And here's the numbers we got. Now, ostensibly, these all came from the same baggie, so they'd be the same. In reality, they look like there's some variety in processing. But this is the numbers you see. In like the 9 samples that they were able to break, because some they just couldn't break, you see that they stretched anywhere from 15 millimeters up to 105 millimeters, right? Now this is an extreme example of variation in failure data, right? But not so dissimilar results can be seen for lots of engineering materials. When you test them, they might last a little while or a really long time. For example, we had solar panels put on my roof, and they're guaranteed for 25 years, and after 2 years, an inverter had already failed, and they were like, oh, that never happens. The average lifetime of these is like 30 years. And then 2 years later, the same inverter failed, right? So, I mean, things happen, okay? You buy an iPhone, and, you know, Apple's making iPhones like crazy, and yet you know that some small fraction of iPhones, right when they take it out of the box, it doesn't work. It has some flaw. Hopefully that's a really small flaw, right? Or it's a small fraction of the time that happens. But in reality, it's going to happen. Failure is something we need to just understand as part of the life that we live in, and understanding variability in data is important. And so what do we do with variability of data? That's what we're going to dive into this chapter. So we'll come back to these numbers in a minute. So first objective for today is figure out what are we going to do with variability as we test data. Second off, we're going to use Weibull probabilistic failure statistics to determine the stresses that will cause arbitrary failure or success rates when subjected to a given stress condition. That's a mouthful. Basically, there is this mathematical approach that under any given stress, if you've done the Weibull approach, you can tell me what should be the failure rate, right? That's interesting because ostensibly we are below the failure strength, right, the yield strength, but realistically speaking, there's some fraction that will fail, and this lets us determine that fraction. Well, it's our best guess at it anyway. So variability is a thing that we have to deal with. It could be due to operator bias, right? For example, the sample that failed at 15, maybe one of these front row Joes like really dug their fingernail into it, and in doing so, they reduced the cross-sectional area because they cut it maybe a little bit, or it created a surface flaw. It's the same thing, right? So now it had a stress concentrator. Maybe the one that stretched to 105, the sample was slipping, and so it wasn't maintaining the boundary condition that you thought. Operator error and sample mistakes during fabrication or testing is something we live with. You can't make and test things perfectly every time. This all leads to error, right? So what do we do with scattering the data, right? How about these two questions? Think about this one. Which one's more useful to you? What's the yield strength of this alloy? Remember, what's the yield strength again? What does that mean? The yield strength is the strength at which, what's happening? Yeah, Landon?
The strength at which it'll break or start to yield or become deformed and you can't like go back.
Yeah.
Stress it beyond that.
Yep.
It'll deform.
Yeah, not necessarily breaking, but the latter part of what you said is all correct. When it starts to deform in a permanent way, meaning it's not going to bounce back, that's yielding. So I could ask you, what's the yield strength? When is this metal going to bend and not bounce back? Or I could say, what's the probability of yielding for this alloy under these circumstances, right? These conditions. That's obviously a much more useful measure, okay? So if we're going to have scatter in the data, we've come up with some sort of ways to address this. The first thing that we do is we talk about averages. It never makes sense to test a single sample and assume that everything's going to be that way, right? We tested 9 samples and we saw numbers between 15 and 105. So how do you talk about those numbers? Like, how do you make sense of it? The first thing you could do is you could report an average. Maybe the one at 15 was an outlier, right? Most of them were maybe around 50, and then you had a couple outliers at the ends. So an average is a much better measure than an individual measurement always. So you should always, and this is, I realize, a no-brainer, but you should always do more than a few measurements. When you guys go to publish your work, a reviewer won't let you publish something that you only tested on 1 or 2 samples because that's not repeatable yet. You don't know if it's repeatable. Now the next thing is, An average isn't the end-all be-all, right? Because let's say I had 9 samples and they all stretched 50 millimeters. The average would be 50. And yet that data set is very different than the data set we have, where the average might be 50, but the range is pretty big. So instead of just an average, you want something to represent the spread in the data as well. And there's lots of tools for doing that. One of the most common is standard deviation. So here's the formula for standard deviation. You've all probably done it in Excel before. You sum up for every single sample what's the individual number minus the average. That's x bar. That's the little hat on it means it's the average. You square that difference. This is called the variance, right? Then you divide that by the number of samples minus 1. Take that whole thing to the square root power, right? That's the formula. That's one of the formulas for standard deviation. There's other ones, okay? That helps. Why does that help us? Well, because if you have a normal distribution, what on earth is a normal distribution? A bell curve. What's that mean? It looks like a bell. It looks like that. It's mathematical. Like this equation is something like exponential. Is it negative x squared or something? It's a mathematical expression. There's no reason to believe that your data will look like a bell curve. Sometimes it does. It often does, but it doesn't have to. If yours doesn't look like that, it's not like there's something wrong. It's just that you can't use this approximation anymore. But if your data is in a normal distribution and you apply a standard deviation, then one standard deviation, either positive deviation or negative deviation, will capture a big chunk of your data. How much? It will capture 34.13 plus 34.13. So about 68% of your data will lie within one standard deviation. All of a sudden, that's a much more useful measure. Think about it. If I was talking about grades on the test, I could say the average was a 65, and the standard deviation was 10. Well, that means that the 68% of the class was between 78 and 58 on the test, right? That's a much more useful measure than just telling you the average, okay? And then this also becomes useful for looking at outliers, because now you can talk about how many standard deviations are you from the average, right? So let's assume that this is iPhone lifetime, right? The average lifetime of an iPhone before it breaks or the battery dies or something, maybe it's 5 years. I know, we were kidding. It's a couple years, right? But somebody out there has an iPhone that's still chugging like 10 years later, right? And some people have it break on basically day 1. So this is a useful metric because you can say the failure of that specific sample was 1, 2, 3 standard deviations or 3 sigmas. Anybody heard of 6 sigma before in industry? Anybody working yet? No? Well, you might get jobs someday, hopefully, and you might hear people talk about 6 sigma black belt. It's this silly name, but it's an interesting concept and it's useful. It was invented, I think, by Jack Welch, the guy, one of the CEOs at GE. He basically said, if you count up how many standard deviations away, 6 sigmas would be something like, right here, 99.99966, right? Or in other words, there'd be 3.4 defects for every million samples. And if you have a really important thing that you cannot have fail, because it's going to kill somebody, like a pacemaker, for example, you would strive for 6 sigma fabrication, right, in your products, so that only 3.4 defects in a million fail. Maybe that number's not even good enough. Maybe it has to be even better than that, right? But the point is, this approach lets you at least define those terms. Now, how on earth did they get to this 3.4 defects per million are going to fail? That's where Weibull Statistics comes in and helps it make it easier for us, okay? So, unfortunately, this is not the norm with engineering. In engineering, it's much more common when we talk about variation in the data to simply do safety factors, right? You've probably done this before. When's the last time where you're like, it really can't fail, so I'm gonna, instead of taking it up to this stress, I'm just gonna divide that by 2 or 3, right? Have you done this? I did this a lot growing up, right? You apply a safety factor. If the little fuel gauge in your vehicle says you can go 10 more miles, you're like, yeah, I don't know, maybe I'll only go 5 more and then I'll fill up, right? You're applying a safety factor, right? You're assuming, so what a safety factor does, well, there's safety factor and there's over-engineering. A safety factor assumes worse performance. So if the spec sheet when you bought it from a provider said, this thing's good to 100 megapascals, you're like, yeah, but I don't believe you. I'm only going to go it up to 50, right? I assume worse performance. Now, the other way to go about this, that's the same thing but a different mindset, is to over-engineer that, and that's to have a design factor built into it, right? And a design factor says, all right, this thing should fail at 100 MPa, so let's over-engineer it so it never sees 100 MPa, it only sees 50 MPa. it's the same sort of idea, but there are two mentalities for it, okay? Is this the right way to go? What's the right safety factor to use? 2, 3, 10? What do you think? What's that? Your boss will say whatever, there's some balance between lawsuits and cost to make these things better, and they literally strike a balance. Unfortunately, that's happening right now. Another hand over there, same thing? Yeah, the fact is engineers do this all the time based off of a gut feeling. Maybe you've tested a bunch of your things and you're like, I ran 20 samples and nothing broke less than 10, so let's call it 5, and that's got to be good, right? That's a safety factor of 2 from your worst performance out of 20 samples. So you're intuitively trying to think about statistics, but we're not doing a good job of it when we trust our gut. We need to be mathematical about this, and that's what Weibull Modulus lets us do. So what it does is the following. It assumes a failure rate F, right? So F is your probability of failure, which is much more useful, because now instead of talking about gut feelings, we're getting probabilistic about this. There's a percentage attached to that. And we can even attach a confidence to that percentage, right? I'm 10%, this thing should fail 10% of the time, and I'm 90% sure of that. That's much more useful. So F is our failure rate. It's going to be equal to 1 minus the exponential of negative sigma F, that's the stress at which it fails, divided by sigma naught, that's going to be a fitting parameter. It's a scaling fitting parameter, right? And this whole thing is raised to the m. That's your Weibull modulus. It's just a fitting parameter, okay? Now, the whole reason that we can use the Weibull modulus is if your data fits to this sort of expression. If you were to plot this, you'd see that this is just an expression that looks kind of like a bell curve. It's essentially a Gaussian. And if you have a sort of Gaussian curve to your data, it will fit really well to this Gaussian mathematical expression, right? Meaning if I turn on the variables that I can tune here, which are, again, 2 of them, I can tune this thing right here, my scaling parameter, and I can tune that thing right there, right? If I have those 2 variables that are tunable, I can fit lots of data sets. It doesn't fit everything though, right? So this isn't going to work for every single circumstance. It works a lot of the time, okay? Okay? What do these numbers actually mean? Well, the sigma naught is sometimes called not only the scaling parameter, but sometimes they call it the characteristic strength. And then the Weibull modulus, what does it mean? A test set that has a higher Weibull modulus is going to have a narrower distribution. A narrower distribution. What do I mean by that? When you take your data, right, and we're going to take the number of samples as a function of when they fail, sigma f, right? Maybe you have a really tight distribution that looks like this. All of them fail like that. And for a different set of testing samples, it looks like that. Again, the average for these might be close to the same number, but one's much tighter together. So it would have a higher Weibull modulus. The red curve would be a large number. And typically for ceramics, if you're doing something like a bend strength, a high number might be something like 20. Whereas if it's a material where there's lots of variation, it's more broad, it's going to be a lower number. Weibull modulus might be less than 7 or 8, right? Okay? Now, just like we've done it before, whenever you see an expression like this that is exponential, and we want to think about it as engineers, we often turn this thing into linear. And we do it just like we've done before. The way that you make that linear is you start taking natural logs. That'll get rid of our exponential. It's also going to bring down the m from an exponent and bring it down. So let's rearrange this equation. So I've just brought the 1 minus 1f over here to this one side. Now equals this. So this is the exact same expression before. We've just done a little bit of algebra to move things to one side. Now we can take natural log of both sides, and that will get rid of the exponential. Now we've got natural log of this thing. The exponential's gone. If we take it one more time, you've got natural log of 1 over 1 minus the failure rate. It's a mouthful. This now equals, this m comes down, and you've got m times the natural log of your the strength at which it fails, minus m times the natural log of your characteristic strength, or your scaling parameter. Okay? Everybody follow this math with me? Okay? So this allows us to plot this in a linear way. All of a sudden, we can linearize this. Okay? We can say that if I plot on my y-axis the natural log of 1 over 1 minus f, right? And on the x-axis, I plot natural log of the stress at which it fails, I should see a linear line, okay? Should be a line, ideally, if your data fits it perfectly, right? And the slope should be equal to m, the Weibull modulus, okay? It doesn't have to go through 0. I sort of drew it arbitrarily. It doesn't have to go through 0. It could be offset. It could be down here. It could be up there. That's the same, okay? Any questions so far on this? Yeah?
So m is the slope?
M is going to be the slope of this line, right? Because you've got over here, this is y equals mx plus b. So this thing right there is x. Therefore, m is just m. It's our slope. Yeah? Question? Because we chose to plot on our x-axis natural log of sigma f as opposed to natural log of sigma naught. That's a good question. Now, when you actually fit your data to this, yeah, question?
Is the right side mx plus b, b depends on m? Like, isn't b supposed to be a constant?
Good, you're right. B is supposed to be a constant, and it is. M is a constant, and this is a scaling parameter, so it's also a constant. Good question, though.
So the x is
This is your variable thing. The stress at which it fails, that's the thing that could be different for different samples. But this, sigma naught, is the same for all samples. It's a great question. Now, ideally, when you fit this, all of your data would lie right on this line. That would mean that the data that you measured is a mathematical perfect fit to this mathematical equation which we came up with of Weibull statistics. That may not be the case, right? It might have some scatter. You could actually put an r-squared value to this and see how well it fits. And if it doesn't fit, then you probably shouldn't trust this because it's going to have it'll have low confidence in the numbers it spits out. But if it fits it okay, let's say the r-squared's better than 0.9 or so, you start having more and more confidence in this as an approach, okay? Everybody with me? Let's do a quick example, okay? So let's take this. We've only tested 8 samples here, so I'm going to generate a bunch of more numbers because typically you only do Weibull modulus an evaluation with something like 20 samples. And I'll show you why that is in a minute. Yeah, question, Pramit?
Yeah, so what exactly is r-squared?
What exactly is r-squared? So let me show you that in just one second. So I'm going to pick a random number between, say, 15 and 100 and let it fill out a bunch more of these, okay? So now we've got 20 samples, okay? Which is sort of the ballpark number you're looking for when you do this, okay? I'm going to grab this, and I'm going to paste it as values just to get rid of those formulas. Okay? Paste it as values. So now that'll get rid of the formulas. I'll delete these. Okay. So the very first thing we do is let's actually try plotting this in a Weibull statistics approach. What do? So we could convert length, that failure, to a stress if we knew what the stress was. But since these guys were pulling it and they didn't have a strain gauge on their fingers, they didn't have the load cell on their fingers, we don't know the stress. But this is the great thing about Weibull modulus and Weibull statistics. You don't have to do it with just stress. If this was like time until failure, years till failure or something, or cycles till failure, the same approach still works. So we can leave it as length. That's okay, right? The first thing we do is we rank these things. So I'm just going to go to sort these things. So home, sort, I'm going to go smallest to largest. We're going to expand the section, okay? So we've sorted our samples, the lowest failure all the way up to the highest failure, okay? Now notice that the sample IDs changed, okay? That's fine. So when we do this, what do we have to do? If we want to go about this, we need to plot on the y-axis. We need to make it natural log of 1 over 1 minus the failure rate. How do we figure out a failure rate? You just seen the data. How do I pull a failure rate out of this? What would you do? I mean, down here, these things were the last ones to fail, so should they have a high or a low failure rate? Should be a low, I guess you'd say, cumulatively speaking, as a high failure rate. Most of your samples by that point have failed. Whereas at the top, very few of your samples have failed, so it's a low failure rate. The way that we quantify this is, there's a couple ways. The most simple way is to do this. Big F, your failure rate, is equal to small n. That's the rank of the sample that failed. What do I mean by rank? Is that the first, the second, the third, or the 20th sample that failed, right? It's the rank, the order in which it failed, minus 1/2 divided by n. So let's plug that in here. we're going to solve for f is equal to the rank at which they failed, right? So let's first type a column for rank, and it's just going to go just like this, all the way down to 20. Now this is going to be equal to, it's going to be the rank of failure minus 0.5 divided by the total number of samples, which was 20, I think. Was it 19? 20. Okay? So when you look at this, all of a sudden we have a low failure rate down here. Or in other words, by the time if I took a brand new sample out of the bag and I stretch it to 15 millimeters, I have a low failure rate. That's a fraction, right? But we could turn that into a percent. We would say it has a 2.5% probability of failing at that point, right? Now, this is not great because we only tested on 20 samples. The more samples you test, the more confidence you would have in that, right? But at least it's better than gut feelings and safety factors. Okay, so now we're going to turn this into the Weibull modulus by plotting, again, natural log of 1 over 1 minus f. So let's plug that in. So this is going to be natural log of 1 over 1 minus f. Okay, I'm going to plug it in, natural log of, of 1 divided by 1 minus this. Okay, everybody with me? I can repeat that for all of those. Now, what do we want on the x-axis? We've now got our y column. Y has been figured out. What do we do for our x-axis? We want natural log of the failure criteria. This was stress, but that could just as easily be time until failure, length, whatever. So we want the natural log of the length at which it failed. So we're going to do natural log of length at failure. Okay? Equals natural log of that right there. Okay? Everybody with me? So now we've got our x and our y. We can go ahead and plot this thing. Okay? So let's do it. Let's grab this column and move it over. Okay? We're going to grab these. Control-Shift down if you don't know how to do that. Save yourself some time. Okay. And that's our data. Okay? So is it a perfect line? No. It's not bad, though. It's better than I thought, actually. We can figure out how good of a line this is by clicking the data here and right-clicking and doing an add trend line. And we're going to put a linear line through it. We want to see the equation and the r-squared value. Okay, there we are. So the r-squared value is 0.93. If it was a perfect fit, r-squared would be 1. You can't have better than r-squared of 1. R-squared is basically a measure of the error, right? If you have this line here, r-squared is calculated by taking each one of these points and seeing how far it is from that line, and then you add it up, basically. So if there was no error, it would collapse to 0. So we don't have that, but 0.93, that's certainly good enough to do some approximations with. All of a sudden, we have Weibull statistics from this because we have that equation, y equals 2.046. The Weibull modulus for this material is 2.046. It's not surprising. All the rubber bands were kind of random and odd-shaped. It doesn't surprise me that there's lots of variability in this data, right? Plus, we put in a bunch of random numbers anyways, right? And then from that minus 8.6227, we could calculate the characteristic strength. Okay? What is this all good for? Why do we do this exercise? Okay? Well, let's say now you did this testing. Your boss said, go figure out the Weibull statistics on this batch of samples. You did it. You come back and you're like, I got the numbers. And now they ask you, all right, we need to have 1 in a million fail. Whatever the application for these rubber bands, it's so important that you can only have 1 in 1 million fail. So instead of what stress should we design for, the question would be, what length should we design for? And let's complicate it. Let's make this a little trickier. Let's do another example here. Okay? I'm going to do the exact same thing, but this time I'm going to introduce a little bit less variation. So I'm going to do length. Let's do this. Okay? So this time let's do that it's a random number. It's going to be a random number between, let's see, how do I do this? Let's do 25 and 50, okay? So it's a smaller range, right? You guys follow me? But the average is definitely lower than before. Let's see if this works, okay? Let's drag this all the way down to here, okay? Oops. To there. Let's grab those and replace it with just values so the formula doesn't keep updating on us. Are there questions so far? Have I lost people? Y'all with me still? Okay. Now let's sort that. Home, sort, small to large. We're not going to expand the selection. I don't want to break the other thing I did before. Did I miss it? Oh, we did it. Okay, great. Right? So now we have a different set of data. We'll call this sample B. So this is length of B, okay? We could figure out the failure rate just like before, right? Failure rate just before is going to be, what is it? It's the exact same as this stuff. It hasn't changed. Because it was just the rank at which it fails. That hasn't changed here. That's still the first sample to fail. Minus 1/2 divided by all the samples. So this is no different. We can just use the same values for F, right? No different. Natural log of 1 over 1 minus F. That's all the exact same, right? Because I only depended on F, and if F was the same, that's the same. Okay? Everybody with me still? Is anybody not with me? Can I answer any questions so far? Okay. Then the last thing we need to do is natural log at the failure of B, right? And this is now going to be equal to natural log of that number. Okay? So let's plot this one and see how it looks. I'm going to grab this column and scooch it over. And on this same plot, we're going to add another data set, select data, add a data set for this will be the B sample set. The X values should be these ones right here, all the way down. Okay? The Y ones should be these ones right here, all the way down. Okay. All right. Perfect. Question is, your boss says we have to have 1 in 1 million fail. Should we use sample A or sample B for this application? How do you answer this question? You've got two different ways of making your sample. One, they have a bigger range, but they tend to go up to a higher value. The other one has a much smaller range, but it seems to be a little more reliable. What do we mean it's reliable? This is your sample B data, orange. It's a higher slope. It has a higher Weibull modulus. It's a tighter distribution. So which one of these should you use? Anybody have an idea? How would you go about this? Turn to your neighbor and tell them how you might approach this. Okay, what do you do? Anybody take a guess? What would you do? Yeah.
The orange one, they fail at a more reliable point.
Yeah, so qualitatively, she's on the right path, right? You're thinking, for the same number of samples, they all failed within a tighter window. So if you were to extrapolate out to now 1 million samples, at least qualitatively speaking so far, it looks like the blue might keep on going down to fail at a really low stress or a really low elongation, whereas orange might not extrapolate out as far. So this all depends on extrapolation, going beyond your data set. That's always a dangerous thing to do because you don't know what it's actually going to do, but it's better than not doing anything, using your gut feeling, which is what we do anyways, right? So how would you get quantitative about it, right? The question was, what was the question? What would the stress be, or what would be the elongation, the max elongation that you should design for? And should it be with sample A or sample B? How do you go about this? Yeah.
Maybe make a normal distribution and like figure out where your 6 sigma is and which one has like a lower stress.
Yep. Instead of doing that, though, let's use the tool that we just developed, right? That's the right idea. We just made a plot like this. Think what this says. Natural log of 1 over 1 minus the failure rate. 1 in a million. That sounds like a failure rate, right? So we know what F is. You want 1 in 1 million to fail. So let's write that down. 1 in 1 million to fail. F is equal to 1 out of 1 e to the 6th. Right? Everybody with me? That's our failure rate, which is some tiny number. Okay? So let's plug that in. Right? Let's plug this into natural log of 1 over 1 minus F. And somebody tell me what that number now is. Somebody have that? Somebody punch that in. I didn't bring my calculator, so somebody else has to. natural log of the natural log of the quantity of 1 over the quantity of 1 minus f. You got to be careful with the parentheses. You'll get burned on this. Negative 13.8. Anyone else getting that? Give me a couple more decimals, would you?
155.
Okay. Okay. Anybody else got something? Anybody get that same thing or not get that? Or there's like 100 people in here. Somebody, surely someone more than Alan did the calculation. Bystander effect in full effect. All right, let's assume that Alan did that right for a minute. Thanks, Alan. And for these two equations, this is our samples A and our samples B. That's our y equals equation, which we pulled off of the best fit of these, okay? So that's y equals 2.046 versus y 0.637. So we know what y is. Y is this number right there, okay? So we could plug that in for y, and we could solve for x. So let's do that. Solve for x for those two. X for A versus x for B. Somebody get those. I should probably assign people. This half of the room get A. This half of the room get B. So actually people do both.
For B, x is
1.5870. That's the value of x? Okay. And what about A? Who did A? What? Negative 2.537. Somebody else get that same thing? Okay. All right. So remember, what are these equal to? What was x in these equations? When we did these equations, the x-axis was natural log of your failure criteria. So we have to set that equal to natural log of the length at failure. Okay? Now tell me what the length of failure is for those two things. So this equals the natural log of the length of failure for A. This is equal to the natural log of the length at failure for B. Everybody with me still? Tell me what those are.
For B, we got 4.8891.
4.88, okay, millimeters. What about A? Let's take e to that number. Yeah. 0.079. Isn't that interesting? Check, this is really valuable. You went from being gut feeling like, if your boss gave you a bag full of rubber bands and says, it is critical that only 1 in a million of these fails, how far can you stretch it? You'd be like, don't stretch it. I don't know. Like, right? You wouldn't know what to do. All of a sudden, we have a pretty good tool. We could calculate for any number you wanted. 1 in a billion, we can do that. Just plug in 1e to the 9 for f, right? I guess 1e to the negative 9 it would be for f, okay? So this is a really powerful tool. Now, this is not perfect. Why is this not perfect? We're assuming that this is going to be the number at which these things will fail. What could go wrong here? What's that? Yeah, ultimately, this is a probability, right? Right? This is a probability. Probabilities, things happen. There's chance there. What else? Your conditions might not change. They might not be the same as under which you tested. We'll get to that in a minute, actually. We're going to talk about moving towards big systems from small systems in a minute. What else? Where else is error involved in this process? The line wasn't a perfect fit, right? We're assuming that the data can be mathematically fit to this funky equation that Sir Weibull came up with, but maybe it doesn't, right? If it doesn't fit to this equation, then you need to find a different approach. If it fits, then great, you can use it, okay? And then think about what this means. Initially, I would have thought the samples that go between 15 and 100, which is much larger, is probably the average. So if you only used average and standard deviation, that would look like the better sample. The other one, remember, it went from 25 to 50. It's much lower average. You would have guessed that the other sample would have been the right one to use. Yeah, Lennon?
So I'm just a little confused as to what those numbers mean in terms of the data. So like with using the set A of data, we find that we can only stretch it to 0.079 millimeters, or 0.079, but with the other one we can stretch it further. Like what is
Yeah, so let me draw it. It'll make it a little clearer, I think. So can I do a pen on here? Yeah, I can, I think. So when I say some failure rate, what I'm really asking you to do is pick a value along the y-axis. Pick a value along here. So let's pick some arbitrary failure rate, right? Let's pick it right here. At that failure rate, whatever that corresponds to, and we could figure it out, you could say natural log of 1 over 1 minus f equals -2, and you could solve for f, and it's some failure rate, okay? But at that failure rate, look at this. Oh, gosh. Windows? All right. Your sample A versus sample B. In this case, A failed at a smaller x value, meaning a smaller length, right? Because the natural log of this value is the length. Whereas B failed at a higher strength. That's the scenario that we just observed. But if you were going to a higher strength, like you want something up here, whatever that failure rate corresponds to, you'd find that your B actually fails before A. So it's not like A is always worse than B. There exists a failure rate at which both would fail at the same stretching. That makes sense? Where these two lines cross, right? If you cross the streams right there, you will have the same failure rate at the same elongation, right? Which is pretty neat. Yeah.
So with the equation ln of 1 over 1 minus f, isn't it impossible to get a number greater than 1 if you use any whole numbers? Which I assume you would in probability, which means that the steeper slope will always
Well, let's just go to our data here for a minute. ln of 1 over 1 minus, so that's this thing right here. Starts out as negative numbers. It does get to positive numbers.
How does it do that?
Takes the natural log twice of 1 over 1 minus f. I don't know mathematically. Double check it, but it works. This is definitely how it's done. So any questions so far on this? This is pretty useful because instead of relying on gut feelings, all of a sudden for any arbitrary failure rate, you know exactly the conditions that probabilistically will get you there. We've already said that this is only as good as the fit to your data, and we don't have perfect fits, and it scales. Your confidence in this prediction scales with how many test points you did. 20 is sort of the minimum. I think I've got a figure that shows why. Let me double check. Oh, dang, I don't have it here. It's in my other class, but maybe we can find it on the internet. I don't know if I'm going to find it. We'll try just once, and then I'll bail on it. Ah, perfect. Okay. Your confidence in this figure here, you're seeing the, okay, so here's your sample size. As you test more and more samples from 10 all the way up to 100, this is your confidence in your characteristic strength, that sigma naught. And a similar plot could be generated for Weibull Modulus, meaning you think that the Weibull Modulus is some value, which you got from the fit, right? We go back to our Excel sheet, and we said, oh, I know my Weibull Modulus because it spit it out up there. But that number, you only have a certain confidence in it. And your confidence increases the more samples you test. So at 20 samples, what's our confidence? Well, it could be between 0.95 times the value, so 5% less. Yeah, all the way up to 105, so 5% more than that value. So that's pretty good. You have a pretty good, basically have like a 10% error on that, okay? And if you were to move out to higher and higher numbers of samples, out to 100, then your confidence is very tight. You have very good confidence in Weibull Statistics working for you, okay? This makes sense? Now, you could have lots and lots of samples and a bad fit, and you don't have that I mean, it's still not working for you. Your average Weibull modulus is determined, but there's still lots of noise in your data. So it all depends on how your data fits a Weibull type of expression. Because of that, we showed you what's called the single parameter Weibull expression. They call it the single parameter Weibull expression because if we go back to Weibull's math up here, this thing, it has the Weibull modulus and one scaling parameter. If your data can't be fit by that, there's other versions of this that have multiple different, that has more parameters. They're harder to fit, but maybe that's what your data needs, right? So we're not going to do that in this class. I just want you to know that it's out there. If your data doesn't fit to this, it's not like you throw your hands up and say, well, we can't use this. It means you have to use a more sophisticated version of it. But this works for a lot of things. A lot of things, and it's valuable because, again, instead of trusting your gut or not knowing which sample, this says definitively which sample you should use under what scenarios. Are you okay with 50% failure, right? At 50% failure, you're going to use, B is going to fail before A, so you're going to use A, right? Anyway, so any questions on this so far? Yeah?
So is your sigma f that you get, is that like saying, if I test 1,000,000 of these, the one that fails first will probably fail at this length?
Yeah.
Okay.
Yeah, that's exactly right. So let's go the other way. I asked you the first question, which is, if you want 1 in 1,000,000 to fail, what should you never stretch it more than for the two different samples? Let's turn that question around now, and let's say, okay, one of the engineers in your plant decides to make it in such a way that it's going to be stretched 30 millimeters. What is going to be your failure rate for both of these test sets, right? For the two materials that you make off the line, what should be the failure rate? If they both get stretched to 30 millimeters, how do you go about this now? You're going to solve for y, because that will give you the failure rate. So you're going to plug in 30, right? So remember, this axis here, your x-axis, this is natural log of your failure rate. So take natural log of 30. Where is that? What's natural log of 30? 3.4?
Yes.
So 3.4 is right here, there. At 3.4, you then take these things. You don't have to read it off the graph. You have an equation. You can plug in that 3.4, right, into your equation. You could solve for y, but we can see it right here that they have different failure rates. At 3.4, B is still failing at a lower rate than A. Sorry, A is at a lower rate than B, excuse me. Right? B is still a worse sample. It's failing before A does. Right? Now, if we said out here, at whatever elongation this is, you can figure out what those failure rates are. Okay? So you can go lots of different directions with this, and it becomes very useful. So if you do a bunch of Weibull testing and you're making iPhones and you know that some of them are going to break, and you basically say, like, it's too expensive for us to make this any better. It's as good as we can make it. You can at least at that point say, this is how many will fail. This is how many warranties we're going to have to service, which is important for your legal team to know, and for you're going to have to pay for those things. So you need to be able to estimate how many returns are going to come back out of the billion that we sell, right? You'll know what fraction approximately will come back to you. Yeah?
You could just do the opposite, which is what iPhone does, and say, we want this thing to fail at least 2%.
I hate to assume the worst in people, but you may be right about that. They may be doing that. Okay, we've got 7 minutes left. Let me shift gears. And like everything, I've got oodles of examples where I go through this slowly and answer all these types of questions on YouTube. Let's do, okay. So it's one thing to test a bunch of really small rubber bands, okay? But what if your actual product is like fan belts on a car? Those are big rubber bands, right? Even if they're made of the exact same material, they aren't, right? But if they were, how would you go from your predictions, your Weibull probabilistic failure predictions on a tiny little sample to something a lot bigger, right? Does it transfer, right? No, of course it won't. You have to scale it. And what's cool is that there's a way to scale this. Here's the equation you use. So the stress of your component means bigger than your test bar, right? So let's say you make like a bunch of little test bars of concrete, little test bars that you can bend and break. But what you really care about is a freeway overpass, right? So the component would be the freeway overpass pillar, okay? That's going to be equal to the test bar strength, right? Then that's going to be multiplied by the quantity of the area of the bar divided by the area of the component, where that's the area associated with the stress being applied to it, right? Then you're going to take that and raise it to the 1 over modulus. Under these conditions, even though these will be different stresses, these will be at the same failure rate. That's the key thing here. Yeah. Bar is like a test bar. Yeah. So again, you in the lab, you made 20 samples and they were little bars and you bent and broke all those and you did your Weibull statistics and you're ready to go. But in the real world, you have to scale that because you're talking about a much bigger thing. Why do we have to scale it? Why shouldn't it be the same exact number? If your bars break at whatever MPa, if you made 20 great big freeway overpass pillars and broke those, why should they be any different? Should they be higher or lower, first off? Remember, stress accounts for cross-sectional area. So stress normalizes the dimensions. So at first glance, you're like, oh, they should be the same, because stress is the force over the area, so it should normalize for dimensions. So why should it be any different? Doesn't have to do with gravity. More volume means more what? You're so close. Somebody say it. Crystal structure. They're just saying crap. Enthalpy. No. A bigger volume means that statistically speaking, you have higher probability of having a critical flaw. Right? Statistics. As you make things, if you make it really, really small, your odds of getting it perfect are better than if you make it gigantic, where there's probably a pore or an eyelash or something in there that might be the critical flaw. So as you go from small to large, things get weaker. In other words, the stress of your component at which it fails will be less than the stress at which your bar fails at some failure rate. Question?
Is that M the same M? Is it the same number?
That's the same Weibull modulus. Yeah, for the same, when you make your sample, as long as you make it the exact same way, right? When you make your test bars, when you make your giant pillars for the overpass, you have to make it the same way or this approach is out the window. If you're sure it's the same material, and the only thing that's different is that you made more of it, then this holds, okay? So this is great. So let's say for a minute that, let's go back to our example. We did our rubber band, and we know the elongation, right? Let's do sample B. We know the elongation at which we get 1 in 1 million to fail. So now let's say that we've got a great big sample, that the area is, I don't know, 100 times more. How many will fail, right? If we did that exact same thing. Or in other words, or let's first do this one. Let's take that exact same elongation, right? And the failure rate that it was at. And if you did a giant fan belt, what would its elongation be to have the same failure rate? Okay, let's plug it in. We would say this. We'd say, okay, the strength of our component, this will be, let's just write it, the length of failure for our component is going to be equal to 4.88 millimeters multiplied by the, what's the difference in area, the effective area and the effective area of the bar and the component? We said it's 1 to 100. So your component is 100 times bigger in the region that's seeing the force, right? The total dimensions don't matter. It's the region that's experiencing the force. Raise that to the 1 over, what was M for that one? M? 6.367? 6.367. You could plug that in. Somebody plug that in for me and tell me what's the length of elongation for our component. And should it be bigger or smaller, be thinking in your brain? Should that be a bigger number or a smaller number? And why? Again, if it's a bigger component, it's 100 times bigger, your odds of having a flaw in there is much, much higher. So this should be a smaller elongation. Yeah. So all of a sudden, you did your Weibull statistics on a bunch of small samples, right? And all of a sudden, you can translate that to a real component. And you know, okay, if I still want 1 in a million to fail, I now know I can even go less. It's only 2.37 millimeters that I can stretch it. Now, this whole exercise today was, I did rubber bands because they're easy to break. But really, when do you do Weibull statistics? It works really well for brittle materials. You can use it for ductile materials, but it's much more effective for brittle materials, ceramics, right? But you can use it for ductile ones. We might say a few more words about this, but there's lots of examples online, and there is a nasty one of these problems on your homework where you're going to have to try this out.